Welcome to the AI Infrastructure Planner. Now this is a short little video just to give you a quick tour of this particular platform, what it does and how you can use it, and maybe explain a couple of the caveats along the way. Now, first things first, this AI Infrastructure Planner is focused on generative AI inferencing workloads. First and foremost, how to size these workloads based on number of concurrent requests, how big those requests are going to be, types of GPUs that you have available to yourself, and the models that you're going to be using. Included in the AI Infrastructure Planner, there are a couple of other modules. So one for vector database sizing, and then a big one being the total cost of ownership calculator, comparing on-premises investment versus cloud investment, specifically using AWS EC2 instances and associated storage services. Another planner is around facility design to help with rack elevation layout. And of course, you can export everything into a nice report. So with that, let's get started with generative AI sizing. So our sizing calculator. Well, within this calculator, you can pick whatever models you want to use. There's a handful that have already been tested a bit more and are good defaults to play with from the Llama series, a couple of mixture models, the Llama 4 series, the mixture of experts models, DeepSeek, and of course, OpenAI's GPT-OSS. So you can play around with these or select another model, pop in whatever other model you want, load it up, and you are good to go. You can also play around with manual inputs of putting in your own config JSONs. So the big thing here is that with these models, this application will go out, it'll go to Hugging Face, and it'll pull down the config JSON. Using the config JSON, it's going to identify the architectural characteristics of the model in order to try and calculate the number of parameters that are going to be used. With the parameter counts, we can identify how much model memory is required, and then also start calculating how much cache or GPU memory is required per token. So when I say cache, specifically I'm talking about the KV cache. So with all of that, then we start thinking about, okay, well, how many of those tokens are we going to need? And this will be based off the number of concurrent requests and the input and output tokens. So the overall context size or sequence length per request. Now, one thing I will call out as a awareness caveat on this particular platform at this particular point in time is that this is focusing on output generation for these requests. What I mean by that, you'll see on the right-hand side, there is an estimated tokens per second. This is not factoring in the pre-fill time of this particular workload, but actually the decode time. So generally speaking, when we're talking about inferencing with large language models, these are going to be bound in performance by that decode phase, which uses the memory bandwidth rather than the TFLOPS of the GPU spec itself. So with that in mind, you could set the number of tokens used, concurrent requests, and that'll give you a global token footprint with which to calculate overall token throughput in tokens per second, but more importantly, the overall memory capacity. So this tool itself is starting first and foremost with how much memory capacity do you need, and then you could start playing around with the inputs and outputs to get a feel for your overall token throughput of your system. You could select from a number of different GPUs, and we've got the Blackwell 300s here. And there is a modifier for GPU efficiency. So of course, as with most production workloads, you are very rarely going to get 100% efficient utilization out of your infrastructure. So you can play around with this modifier, but 70% is usually a good ballpark to play in. So once you have all of that, you can look to the size and see what kind of sizing results you've got. Now you can import this directly into the TCO analysis tool, which will create a very simple, call it, calculation using the number of servers to support 177 GPUs in this case, and then a comparative amount of cloud instances to support the same amount of capacity, ideally using the same family generation of GPUs. So let's do that right now. Using the TCO tool, and it's going to pop us in, and we can see that it'll take about 23 servers in order to accommodate 177 GPUs, assuming 8 GPUs per server. So for on-premises comparisons, there are control nodes, some storage nodes, some inter-GPU switches for the back-end fabric, and then optics for that back-end fabric as well. There are some hardware maintenance costs, estimated around 10%, some software, personnel, and facilities costs in terms of power, cooling, and rack capacity. On the cloud front, you have your AWS region. You could enable SageMaker or not. That's going to be a 15% premium on the EC2 instance cost. There are different pricing models, of course, so on-demand, reserved, 1 year, 3 year, and spot. And then you could fine-tune any additional discount from there. Enterprise support as well, and then some default storage services as well. So that is the cloud side of the house. Let's show you at the very top what this TCO breakdown looks like. So first thing you'll notice is that a big warning that this is a Blackwell 300 system, which is not yet available at the time of recording this in AWS. So we're going to use the B200 equivalent and then add a 30% premium due to just recency bias on the newer platforms. If we were to go down and swap what the GPU may be, then you'd see that warning goes away, and we're using the actual correct instance and then determining the current live price and then discounting that based on the pricing model that we use. So with all of this in mind, there are a couple of different presets that you can play around with. So let's say that you didn't use Gen AI sizing, then you could pop in here and we got a couple of different presets that you're able to play around with. So we have those. Now, once you have the full cluster that you're working with, the next logical step is, okay, if I'm going to invest in on-premises infrastructure, I need to know what my data center is going to look like. And this is where the facility design comes in. So we'll clear out my previous input. And you can see first thing here, when you are working with an empty slate, then you could actually import from the TCO analysis, and it's just going to lay out your network racks, storage, management, compute, etc. This is a starting point, and it's going to be based off the power available per rack as well as the RUs available in those racks. So if we were to clear this out, have the same TCO input, but drop this down to a 30 kilowatt rack and then do an import, you'll see the layout is much different than as a starting point. And of course, if you wanted to, say, move around some of the network devices, storage devices, some of those control servers, whatever you want to do, you could play around with those, or drag and drop from the list off to the side and drop those in as well. So once you've gone through all of this, then you could come into the results pane, and this is a nice static summarized view of everything that was configured thus far. Big point of order here. No, we didn't mess around with vector database sizing. So what if we were to go back and do that and say, okay, document size in gigabytes, and we've got 10 gigabytes worth of data that we want to embed in a vector database and use as part of some sort of RAG-based architecture. So we can do that. Memory mode, we'll keep it hybrid and try to keep most of this not in memory, but we could see 10 gigs of documents embedded in a vector database. We're going to need around, including replication and backup, almost 200 gigabytes of memory there, or capacity rather. So do keep this in mind. At this point in time, this is not factored into the TCO, as the assumption is this would live on system memory or on disk of the existing servers, and that there is prerequisite capacity on those devices included in your storage, in your either storage servers or in the actual compute nodes that you're using. So let's go here, do a quick export and organization name. We'll go with the tried and true classic Acme and then Acme AI project. So we'll generate this report, give it a moment, and then we can see what that looks like. There we go. So now we have the report, And here it is, prepared for Acme, the Acme project. Name of the report, analysis period, we were doing 3 years, the date, and then we have the overall TCO that is used. Savings amount with a recommendation, in this case on premises over 3 years was more cost effective than going in the cloud. We have a breakdown of all of the costs that went into the calculations for both on-prem and the equivalent cloud infrastructure. The sizing results, so number of GPUs, system used, etc. And then we have the overall facility design. And this will just give a quick summary of what was in the actual racks. So the name of the racks, the equipment in those racks, power draw, utilization, etc., etc. So with that, you've got a full report that you can use for your infrastructure analysis, business cases, whatever you desire.